It's the beginning of a new era in astronomy. For the first time, scientists have discovered ghostly particles that are not just extraterrestrial, but extragalactic. They come from millions of light years away, from where stars explode or supermassive black holes swallow cosmic matter in tremendous vortexes. Neutrinos. They are the most common elementary particles that exist, and the most mysterious. Every second, 100 billion of them race at a speed approaching the speed of light through our bodies without our ever noticing. They move unimpaired through the universe because they can fly easily through anything.
For me, the neutrino is the closest thing to nothing we can imagine. It has zero size, zero charge, mass very close to zero, and it interacts so weakly with everything. But somehow or other, the neutrino isn't nothing. It might be the key to the universe.
For astrophysicists, the universe is one huge laboratory in which most things still have to be discovered. The matter of which the stars, planets, interstellar gas clouds, and humans are composed only accounts for a mere 5% of the universe's mass. The rest is an enormous, unsolved puzzle. The human eye is woefully inadequate to see everything in the universe. Astrophysicists are looking for apparatus that will help them investigate the tremendous events in the cosmos, for which they have any number of theories, but precious little concrete information. They are not simply neutrinos, in our case, neutrinos with particularly high energy. They are neutrinos conveying a message. They're ambassadors. They tell us something about the object from which they come to us. This object must be something in which incredibly high energy is released, many times higher than that in the Sun. We're looking, for instance, at neutrinos from the destructive processes of dark matter. Possibly these neutrinos will give us an indication of what dark matter is. Ten years ago, an international team of scientists started to build a gigantic detector to catch these high-energy neutrinos in one of the most remote places in the world, the South Pole. Deep in the ice, the scientists are looking for the flashes of light that a neutrino releases when it collides with matter. With a mobile drilling station, the research team has melted countless holes kilometers deep into the Antarctic ice cap. Here, the ice is so deep and pure that the detector, which measures a cubic kilometer, has sufficient space and ideal conditions. A hot water drill, which draws down its own weight as it melts the ice, has prepared the way for photosensors in the crystal clear ice. The upper layer of the ice sheet consists of snow. The snowflakes change as they are pressed down deeper and deeper over many thousands of years, from graceful ice crystals to compact, transparent ice. The meter-high flakes are transformed into firn, a layer of compacting ice. More and more snow presses the air out of the firn. It becomes denser and even more compact, until finally it is a body of ice almost free of air. The scientists have introduced photosensors the size of basketballs into the ice, on separate strings like threaded beads, up to a depth of 2.5 kilometers. Within a single day, the drill hole freezes closed.
Yeah.
When the work's completed, a cubic kilometer of ice is full of sensors.
Yeah, there we go.
The gigantic detector is now ready. Deep within the crystal-clear ice, where it is pitch dark, thousands of highly sensitive photosensors wait for minimal but far-reaching traces of light. And these traces only occur when a neutrino collides with an ice atom. In 2013, scientists first discovered conspicuous traces of light in the IceCube detector.
Das Neutrino selbst kann man nicht fangen. Nicht? Das Neutrino.
We can't catch the neutrino itself. It interacts with matter very rarely. A reaction of that kind only occurs in our detector if we're very lucky. Then it reacts with an ice atom and releases secondary particles, which move hundreds of meters through the ice. Behind them, they draw a ball of light, which is called Cherenkov light, after the man who discovered it. And it's this that we identify with the IceCube. We have succeeded in identifying high-energy neutrinos for the first time. Ernie and Bert. They had such high energy that it was extremely unlikely that they were created in the Earth's atmosphere. These neutrinos must have come from outside our solar system. When a cosmic neutrino, which is much smaller than the nucleus of an atom, collides with an ice atom, it leaves behind a trace of light that spreads over several hundred meters. The scientists call their discoveries Ernie and Bert, the breakthrough after decades of research. All over the world, scientists are searching for these messenger particles from the distant universe. Also on the other side of the planet, in Europe, a research institute on the French coast, southwest of Toulon, is the base for a tremendous Mediterranean project. This building was constructed in the 19th century. Now it captures the data of minuscule flashes from the sea. Here researchers are trying to decode the neutrino's oscillations, their transformation into three so-called flavors on their flight path. Antares, the small prototype of a neutrino deep-sea detector off the coast of southern France. It's already sending data. It's still a prototype. Within a few decades, a cubic kilometer large detector field is planned. KM3 net.
Each box corresponds to one of the detection strings. Each cross represents the height and the time of the photon that was detected. So on these displays, we can see a kind of time history of the counting rates on the optical modules. The main source of light that we detect is from the natural radioactivity of the salt. The potassium-40 isotope of the salt emits a little beta particle which emits light. So most of this light is just due to this natural radioactivity in the sea. But every now and then we may get a fluctuation or a spike in the time chart, and that is associated with bioluminescence activity. In the sea, the organisms have evolved to emit their own light, bioluminescence, and if one of those organisms comes close to the telescope, it could even bump into the telescope and go ouch and make a flash of light in reaction.
Nous avons étudié les corrélations entre la...
The aim of our research into bioluminescence is the connection between bioluminescence values and the physical parameters of the Mediterranean, which is a small ocean. Especially the temperature and the salt content have a great effect on the behavior, the movement patterns, the mixing ratio and currents of the water masses. We want to understand these dependencies better.
La direction du courant.
KM3 net will be a multifunctional measuring instrument in the sea, supplying biologists, geologists, and physicists with data. Apart from neutrinos, the scientists can already detect specific species of whales and dolphins in the Mediterranean.
Donc là, vous avez sur cette bande.
Here's the expired time, and in the verticals I can read the sound frequencies.
Et donc, chaque fois qu'il y a un signal,
Each time a signal is detected, I see a color code and hear a click. So I can hear short broadband signals, clicks, in real time, a few milliseconds after the dolphins or whales, especially toothed whales and sperm whales transmit them.